Okay, we're going to spend some time comparing and contrasting the two theories. We have valence bond theory on the one hand and molecular orbital theory on the other. The entire point of this lesson is to compare those two theories, valence bond theory versus molecular orbital theory. We just finished the one. We don't want to get it confused with the other. Valence bond theory considers bonds as localized between one pair of atoms, where molecular orbital theory considers electrons delocalized throughout the entire molecule. This is an important distinction which results in differing properties that each theory can predict. So valence bond theory did a nice job predicting polarity and structure. Molecular orbital theory will predict things like magnetic properties, electrical properties, and thermal properties. Valence bond theory creates bonds from the overlap of atomic orbitals, and it makes hybrid orbitals out of those atomic orbitals. All of the orbitals involved are on the central atom. Okay, that's how we keep our bond localized. All of the hybrid orbitals are on the central atom. As an underlying assumption in molecular orbital theory, the solutions are delocalized. So they're considered molecular orbitals, as in, therefore, the molecule, and they come from two different atoms. They combine atomic orbitals to form molecular orbitals. They are given the designations sigma, sigma star, pi, and pi star. The sigma and pi designations mean something similar in both theories, but they're not exactly the same. We'll get into that more with the next point. Valence bond theory forms sigma or pi bonds. Molecular orbital theory creates bonding and antibonding interactions based on which orbitals are filled. What is that talking about? Okay, if you watch this after you've watched the molecular orbital theory one, then this will make total sense, and if not, you may want to go visit that next. Here we go. Sigma bonds are an orbital overlap on the bonding axis or internuclear axis, which is what we're going to call it from now on. Pi bonds overlap around the internuclear axis. Molecular orbital theory describes delocalized orbitals, so instead they call them bonding and antibonding, and they give them different shapes depending on what type of orbital it is. The sigma designation for molecular orbital theory is a bond along the internuclear axis, which is, we form a bond along the internuclear axis with valence bond theory as well. But it's coming from two different, like the hybrid orbital and the atomic orbital on the other atom, whereas molecular orbital theory, it's the molecular orbital itself is the whole shebang. The sigma star is the antibonding orbital where the electron density has a node between the nuclei and is instead that electron density is located along that internuclear axis, but it's on the outside, the side not shared with the other nucleus. Pi orbitals are still made from p orbitals lined up to overlap above and below the internuclear axis, but we also have antibonding version where the electron density is located outside of that area entirely. It's not between the nuclei, there's a node there. Again, it makes more sense with pictures, so hopefully you've gone up through the molecular orbital theory presentation first. Valence bond theory predicts molecular shape based on the number of regions of electron density, whereas molecular orbital theory is really good at predicting the arrangement of electrons in molecules. Okay, so this is why they work for different things. Valence bond theory gives you structure. Like, that's its job. That's what it was designed to do, and it does a nice job of it, and it predicts polarity because of that. Molecular orbital theory predicts the arrangement of electrons in the molecules, which results in the ability to predict electrical, thermal, and magnetic properties. You can't get that from valence bond theory and VSEPR. It doesn't work. Finally, valence bond theory needs multiple structures to describe resonance, but molecular orbital theory does not. So in valence bond theory, you have to have one with, a sigma on everything and a pi bond on one, and then you switch up where the location of the pi bond is in the different resonance structures. In molecular orbital theory, it already has delocalized electrons, so we don't have to describe all of those options. We just have the one where we're like, It's delocalized. Wah, there it is. Okay. All right, to summarize our most important points, valence bond theory comes from mixing atomic orbitals on the central atom to make hybrid orbitals. Molecular orbital theory comes from mixing atomic orbitals on two different atoms to form molecular orbitals which have delocalized electrons. Valence bond theory predicts structure and polarity, while molecular orbital theory predicts magnetic, electrical, and thermal properties. Molecular orbital theory has bonding and anti-bonding orbitals where the electron density is between two nuclei in the bonding case and has a node perpendicular to the internuclear axis between the nuclei in the anti-bonding case.